Okay, let's see if this works this week. All right. So again, like I said, I want to kind of talk through this idea of what we call construction technology. Okay, so it's not in my mind, it's not always about just the tools, right? It's not just about software, but it's a lot of changes in construction methods, materials, all this type of stuff that plays into it. So I really want to take this kind of historical look at construction technology and talk about some of these kind of main principles and ideas we're going for, right? So again, construction has always been a technology industry, right? Um, Technology can change the purpose, or sorry, technology changes, but the purpose stays, really consistent. Okay, builders look for ways to control materials, organize labor, move heavy things, communicate intent, and really reduce uncertainty on a job site, right? So, you know, this image up here that we're looking at just is fun. Yeah, I made AI to make it. It's fine. Uh, it's showing you this really, dichotomy here of, we're still on both sides of this creating a building. Okay. On one side, you have kind of old techniques of building, different types of structure, different infill, different labor force than you see on the right. On the right, you're seeing now we've got more connected job sites. We've got different technologies, different crane technologies for how we can move things. It really just changes over time of what we're capable of doing, right? So, ancient builders coordinated stone, timber, concrete, labor and geometry. Industrial builders, added in the iron and steel. Steam power came into play. Mass production was a big deal that kind of moved things forward. And then you kind of move into contemporary teams where you add that digital workflow, right? So again, a lot of stuff we're going to talk about this semester is the digital kind of aspect and how that plays into what we do. So again, contemporary stuff moves into that. Mobile information, we have cell phones, sensors come into play, all these different connected workflows and also connected building functions, right? That then require more coordination needs. Okay, so some things weren't needed back in the day. Now you have buildings that are smart buildings. They have a lot more stuff involved in them. A lot more coordination has to go into that between the systems. I mean, heck, you didn't have HVAC back in some days whenever you built buildings, right? Now we have to coordinate with HVAC. We have to deal with all that information that's in there as we get moving on. So hopefully by the end of this, you're really just able to kind of look at the historical structure and ask more questions like, what does it look like? What technology made that possible? What problem did it solve? Or what did it change for the people, after it was built? And this kind of ties into your writing assignment that's going to happen this week too, just to give you a sense of that. So, okay, so before we get kind of the overall, historical kind of timeline here, let's kind of define technology in a different way here, right? So, everyday conversation of technology often means, like I said, electronics and software. When I usually say that, people are always thinking, oh, it's the software I used or the specific tool that I used. But I really want people to understand that it includes really the materials, the tools, a machine, a process, a labor system, or really an information method. And that's what a team can reliably build on, right? Ask yourself a couple questions with this. One, what materials were available when we're talking historically, kind of thinking back, right? What materials are actually available? Stone lintel, maybe a timber truss, concrete arches. If you think through the kind of the history of construction, all these different things change the way we're able to build based on span heights, span lengths. Think about the methods of how we work, right? So before we had formwork or what was used for formwork to modern day scaffolding, thinking about standard dimensions, prefabrication now is a big part of construction. We do a lot of prefab work where things are built in a shop and then shipped out the site. So you have parts and pieces of a building that might be completely prefabbed in a warehouse and then sent out to the site. And then, you know, how does information kind of get around on a job site? So we have sometimes full scale templates. It was really important, back in the day whenever we were building stuff to have a scale model, like a really detailed craftsman scale model of a building. And the reason for that was a physical model. Okay, not a digital model, but a physical model was used in heavy detail to give the craftsman the understanding of what was expected on the actual built building, right? Nowadays, we have digital models, right? Where we add maybe not as much detail, but we add a lot of information in these digital models that then are going to be used to inform the contractor of how things are going to actually get built. So it's just understanding those different methods and tools. Measure drawings. We started moving into more of this idea of blueprints. First done by hand, then by CAD. Then again, in this world of kind of building information modeling, they're all technologies for just transferring intent, right? That's kind of the whole point here. Is how we're moving this information back and forth. So let's see. Let's just get to the next slide here. Okay, so we're going to kind of look at these 5 forces throughout this whole section here when we talk about this. Okay, it's really the framework for this. So materials really are determining the strength, the durability, fire resistance, the weight and the form that can actually be made. Tools are really what's extending the human force and precision. Labors, including not only the number of workers, but also the specialization, the training, the supervision, the safety practices. Transportation controls are where materials can really where they come from, how large components can be. And then again, information is controlling how we accurately share these decisions with the team, right? So all of these things play into this as far as how we're getting work done. The most important historical changes usually combine several of these together. Okay, so when you think about it, the Industrial Revolution didn't transform construction just because iron existed, right? It's a big thing to note. Iron had been used for centuries, right? The change came when we improved production made iron more available. Right, so it wasn't necessarily just iron; it's just other technological improvements that were able to kind of move things forward. Transportation networks also, moved it. Factories produce repeatable components. You get more standard components, standard things you put out there. Engineers came up with new calculations, and then also new crane technology help hoist assemblies and hoist and move that material in new ways. Right, so all of those things together are what are really shaping technological advances. So the same logic applies to digital construction, right? A model alone does not transform a project. A team still needs hardware, they need software, they need standards, they need people that understand the process in a way to deliver that reliable information to the field, right? Every technology, it's not that it's just getting rid of people that did things before. You're now needing new roles, new ways of working, new skill sets that people have to learn, right? All right, so let's get into kind of the general. If I may give it a timeline here, right? So this is a pretty broad timeline. It's really not a straight line though. Whenever you think about it, okay. So construction history doesn't follow that kind of straight line pattern, where one era just suddenly replaces another. Ancient masonry is still, or practices are still used. I got a mason here, right? Who's my mason? Got a mason, yeah. So, there's still some things you do that have been done for a long time, and it hasn't changed because you don't necessarily need something. So, we've had things that are consistent across the board. Builders used to develop durable systems around local materials and accumulated craft knowledge. The industrial area really, increased production and transportation, so it just making components and machines available at new scales. While 20th century construction mechanized, with standards, codes, hate codes. That slowed a lot of stuff down with codes, but that's right. Standardized codes, highways, utilities, large organizations came into play there that impacted, how construction had to get done and needed to be done, right? We used to live in the era of what they called the master builder. I remember, learning about this even in architecture, that, it was more this master builder and kind of master craftsmanship quality that came to buildings. Whereas once you started getting organizations like the AIA and different code officials in and all these safety procedures, which are all good things, there's nothing wrong with them. The idea that we have OSHA and we have safer job sites is highly beneficial. But all of those things have more requirements. There's more things needed now in the drawings. There's more expertise that's going to be needed to actually get things done. So just notice this timeline kind of moves from controlling physical materials towards controlling increasingly complex systems and information. Okay, that doesn't mean physical skill becomes unimportant. It just means the number of relationships that must be coordinated grows. A modern building still needs or still depends on concrete curing, steel connections, waterproofing of the building, and safe work. It also depends on hundreds of drawings, models, specifications, submittals, schedules, and field decisions staying all aligned. So this is just why it's kind of important to study history and understand where we kind of came from, and that, how and when new technology enters an existing network of people, materials, and practices, and kind of what drove those factors is good to kind of understand. So maybe some fun examples, some things you might be familiar with as we're working through here. So this is just, if you don't know, this is the Pantheon. It's a powerful case, in really material and different technological advances, right? It combines material, geometry, temporary works, and a real construction sequence here, right? So this is dedicated back in 128 CE. It still contains the world's largest unreinforced concrete dome. Kind of crazy to think about that, right? This was built a long time ago, but still actually is the largest unreinforced concrete dome. It's not simply a giant mass of one concrete mixture. So pretty interesting. Like Roman builders reduced the weight towards the oculus. So they actually changed the mix of concrete as it went up towards that big opening, the oculus at the top. They changed the aggregate. They changed the thickness of the concrete. The geometry also directs the compression through the dome and into the supporting drum, right? So there's a lot of structural kind of engineering to this in a sense. But, even imagine this building, okay? If you've seen pictures of this, a very large building, huge oculus. Even think about the complexities of that with modern day tools, okay? With concrete pumps. We have concrete pumps that can pump concrete up to high heights on multiple story buildings, all that. Think about that back then. They didn't have concrete pumps. So how did they move material around? How did they actually mix? They didn't have mixing trucks of concrete coming to their job site. They had to deal with it on site, right? So think about the volume of material that was used to actually do this. Even with modern day stuff that we have, think about what they actually had to deal with back then, right? So all of those things, the finished form of this is really just evidence of an entire construction system, not just an architectural idea, which is always interesting. Think about this. You look at this, the coffers that are up here on the screen, all of these like indented, coffers, right? That looks like kind of an architectural aesthetic element, right? It looks nice to the eyes. But what that is also doing is not just an eye pleaser, but it's also reducing the overall weight. You think about that. It's, form follows function in this case, right? So these coffers up here are actually reducing the total need of concrete, the total weight of concrete. So it's helping the structure of this entire thing as we go forward. So pretty interesting. Having the oculus at the top also is removing a bunch of weight, at the crown by also admitting light into the building. Again, just a good example of design and construction really reinforcing one another. Lots of principles around that. People say that, when design and construction techniques are going in, or the idea of form follows function is always a good thing to see. And usually you see some pretty good architecture when that happens. The lesson here, I think, is that, material innovations themselves are rarely isolated, right? Concrete enabled the dome, but formwork, geometry, aggregate selection, logistics, and accumulated craft knowledge made the concrete usable at this scale, right? So lots of things went into this. It wasn't just one thing. It wasn't just a material. It wasn't just one way of working. Lots of different elements kind of played into this. And again, no computers yet. We're not there yet. Okay. Here's just some ideas. Kind of the idea of concrete itself is always looked at as a pretty big historical technological change, right? I think in some of your readings that are out there, we looked at an example where MIT kind of researched or revisited a detail that earlier observers often treated as evidence of poor mixing, right? So they looked at these white lime clasts inside Roman concrete. And their analysis really suggests that Romans used quick lime in a hot mixing process, and that process formed reactive calcium-rich features within the material. Okay, so the proposed self-healing mechanism works kind of like, a small crack develops, water enters, the water reacts with the calcium source in a lime-classed calcium carbonate, then recrystallizes and fills the cracks in the laboratory tests described by MIT. Cracks in a hot mix samples healed within 2 weeks at the point that water no longer flowed through them, while comparison samples without quicklime did not heal in the same way. Okay, the important thing to kind of think about here is not that we should simply just copy an ancient recipe. Okay, is that, it can really inform what's going, but now with new technology, we're able to re-examine some of the things that worked well or some of the things that failed, right? So with new technology, we're able to go back and kind of study, why did that work? Why did that work well? Or why did we have problems with certain? We do this all the time, even in modern building. You're going to have lessons, what we call lessons learned. If you work for a contractor, I'm sure you've got those all the time about what went wrong on a job site. Here's why it happened. Here's how we can fix it, and how we're gonna learn from it in the future as we go forward. So that's always happening, constant kind of conversation on job sites. Yeah, a quick note here that this is also really a sustainability question, right? So if a concrete structure lasts longer, it may need less repair, replacement, demolition, and new material over its life. But a historic technique can therefore influence very current problems, right? So concrete is one of the age-old materials that we hear about in construction. It's changed. There's different ways now. There's so much science behind the way we mix things, the way you can have additives to your concrete mixes to help in certain situations. So it's a technology in and of itself that's not directly a computer technology, but there's also a lot of computer technology that's involved in how we get to the end state and when we use concrete. Concrete can make or break a job. That's a big deal. If scheduling's not done right, if you have a bunch of concrete trucks coming up to your job site, delivered one morning, if your team's not ready to go, you could waste a whole lot of money in concrete because it's on a deadline. Those trucks come, they're ready to go. They don't have time to sit around and wait. You can't tell them to come back tomorrow. So there's a lot of sequencing that has to go around this type of stuff too. So, speaking about iron and kind of moving forward into the industrial age, right? And thinking about how iron influenced design, how it's changed and shaped things over time. This is just an example of the Iron Bridge in Schroersfire. I can never say it correctly. This opened in 1781, right? So moving a lot farther forward than the Pantheon. But this became really an early demonstration that cast iron could serve as a primary structure. Okay, structural material at an architectural scale. So it spanned the river Severn using cast components produced in an industrial region known for iron making. So again, going and finding the right skill labor that could actually do it. But again, kind of look at the form that we've got going on here in this. Okay, so the bridge is iron, right? But many of the connections resemble timber joinery. When you look at it, some of that stuff looks kind of like, stuff you would see in like a wood building, right? So oftentimes you get builders that understand a new material by adapting familiar forms and methods, okay, that can help innovation become buildable, even if later engineers discover more efficient ways to use the material. So you might look at that now and think that's kind of ornate, right? So it's like those joints are more ornate, they're more visually pleasing, where you could have easily accomplished that nowadays with, steel L sections. But that's always kind of we learn from what we've known in the past and kind of can adapt that to what we're doing. So it also represents really a shift in where construction happens. So when components can actually be cast in repeatable shapes away from the final location, so that early idea of shop building or pre-manufacturing, right? So if we can build pieces of it and then bring it to the site to construct, it's moving more of that to that production environment. So the site becomes a place really of assembly as well as fabrication. But this idea will really kind of reappear, when we talk about prefabrication, structural steel, precast concrete, all those types of things kind of play into that as well. Okay, questions so far? Yeah, doing good. Staying with me. I know it's history. You didn't think you were gonna have a history class in here, did you? But it's part of it. We have to understand kind of where we came from. This is moving a little bit further forward. This is Shrewsbury Flax Mill, the Maltings, right? So they used cast iron columns and beams inside a brick exterior. This actually is usually described as like the grandparent of skyscrapers. Okay, and again, looking at it like that's not a skyscraper. It's just a big building. Okay, but again, completed in 1797. The main mill here was used for that cast iron columns and beams, brick veneer. The big problem they had here was industrial fire risk. Okay, this was a textile mill in the time, and they always contained highly combustible fibers and really relied heavily on timber floors and framing. Replacing the key structural members with iron reduced the amount of combustible structure, right? So being able to move from a lot of timber to actually using a lot of, steel in here was able to help lower that risk of combustibility. So the longer kind of term significance here with the frame, right? So we also now are looking at using a skeletal structure, right? So not relying on the exterior members of this to support the overall building, but now you have kind of a skeletal structure inside the building that's actually carrying the weight of the building. Later builders could really refine that material, the connection, the fire protection, and the load analysis, eventually using steel frames to carry tall buildings, while exterior walls became lighter enclosures. So you think about the modern day skyscraper, it's, the core and the structural framing of that's what's really carrying the weight. A lot of times those big glass facades and everything else you see are just more lightweight kind of attachments, right? They're hanging off the structure in a sense, as you look at taller buildings now. So this is really just a good example of, innovation solving one problem and opening, a door for another one, right? So the original purpose here wasn't to invent a skyscraper. It was just to deal with more fire resistant, materials. So that concept that they built in order to do that later led to the innovation of now we can actually build taller, higher skyscrapers, right? So when you're looking in the written assignment, I want you to think about these different kind of ways of some of these projects have a kind of a layered approach to the technology evolution, right? So it's not always just, now that we had software, we were able to do this, or because of software. But think about some of the other things that were technological advances in that building specifically, and how it kind of maybe changed things in a layered kind of way of looking at it. Okay, so this is just so steam power. If we're looking kind of now at the idea of internal combustion, electric engines or electric machines changed kind of the effort level that we have in construction job sites, right? So excavation is a clear example. Okay, when we see you think about hand excavation or people having to move earth and dirt around job sites requires a lot of people, large workforce, and they're able to move relatively small amounts of material, right? In comes the steam shovel when they were early invented, or now we have massive machines that can move just absolutely metric tons of dirt at a time, that are able to kind of change the way we work and move things further, right? But again, with things like the steam shovel or the mechanical equipment we have today now requires a skilled operator, so someone has to be trained on that machine to be able to operate it. There's still a human that's involved in that. There's fuel costs now to it, maintenance costs to it. You have to transport that equipment. So this equipment's large. You have to get it to a job site. It's not just your workforce showing up, and now you got to get large pieces of equipment transferred from one job site to another. So that comes into play. And again, you have to make sure you have work plans that are actually suited to the machine, how it can move around the site. All of those types of things have to be taken into consideration. Again, mechanization does not simply remove labor. Okay, just because we have machines that can do things now, it doesn't necessarily remove labor, it just changes it. Okay, so we move from, the roles where we might have had a lot of people moving dirt to now we have operators and mechanics, planners, surveyors, supervisors. The pace of that downstream work usually has to change with it too, right, with the going times. And this is an important conversation, even in today's world of construction and where things are going. We've for years, for decades, I think now we constantly talk about this shortage of skilled labor, right? The shortage of skilled labor in the construction workforce. They're worried that we're never going to be able to even make up the gap, even with incentives of getting people into skilled labor. And it's true. There's a massive shortage. So the topic of robotics, which we'll talk about later, is coming into play here. So the idea of AI and robotics is going to come into play. And I think it is going to have another one of those transformative kind of approaches to construction, to where there's going to be more things that are prefabricated. There's going to be more things that are going to be able to be done by robotics and automation. Again, because we have to get rid of this exhaustive process of losing skilled labor out of the workforce and trying to bring new people in. They're at a point now that they've been at a point for a while where there's really, I don't think, a way to overcome the gap in that, and we're just running out of skilled labor people to even be able to fill those spots in. So I think it's going to be interesting to see what happens with that as we're moving on here. How many of you have a job you think could be done by a robot? Just I'm just curious. Bricklaying. They already have some out there right now. Yeah. Anybody else? How many of you be okay if a robot took over your current manual labor job? And you were able to do something else? Maybe. Again, it's a dynamic, right? So the thought there is like, well, there's certain aspects, and I mean, it's with me too. Like, there's certain aspects of my job I wouldn't mind at all if it was automated out and AI took it over or did it. There's other parts that I still want to be involved in the output or the input in what's there. So I think that's just kind of something to think about as we're going through all this. Okay, here's another one. Let's the Crystal Palace, if you don't know this one. Right, so moving a little bit further, 1851, right? So this was great. This is built for the Great Exhibition of 1851, right? So, and it really demonstrates when construction adopts that manufacturing mindset. So again, we talked about, manufacturing things offsite to bring it to site. This was a great example of that. So instead of treating every part as really a unique craft object, the project organized production around repeatable bays and pieces that could be fabricated and assembled quickly. Usually for these types of things, when you're talking about like the Great Exhibition, you think about the Olympics when they build buildings for this, there's always technology advances that happen during those times, because usually this stuff has to be built quick. They don't have a lot of time. They want to do something that really is great, but they need it done fast. So it usually drives innovation in times like that. So again, this was the same thing happened here. The date of this exhibition created a really hard schedule for constraints. So the idea of standardization really helped the team produce parts in parallel that turned the site into an assembly operation. So instead of completely doing everything on site, it was more of an assembly that happened on the site. After the exhibition was over, the building was dismantled and reconstructed, at a different location, showing that the system was not permanently tied to its first location, which is pretty interesting. So this idea of kind of a kit of parts, kind of like Lego type building construction, kind of interesting. So it doesn't mean that prefabrication is just automatically easy, It's not. The prefabrication can sound great and sounds like it can save a lot of time, but the level of coordination that goes into prefabrication is that much higher. We can't, at that point when you're dealing with prefabrication, it has got to be locked down and figured out before it goes to the shop to get built. Once it's built and you have that part that's being produced there, you can't make changes like you might have done in the field, right? So prefabrication actually is demanding a higher level of kind of standard, a higher level of coordination to be able to get things done. So mistakes in that, repeated across hundreds of components can really become more serious than, one-off field adjustments that we usually deal with. Okay. So 20th century, right? Now we're starting to really connect machines, the standards now that we have to follow, and there's standard ways of doing things, and then kind of scale, right? So we're getting more vertical. We've got these steel frames. We're introducing elevators. Imagine that. Elevators weren't a thing. Fire protection now. We get really tall buildings. We're dealing with all of that. In the horizontal aspect, we've got large earth moving equipment. We're dealing with paving now, right? Large bridges, large form bridges to connect things, and then lots of logistics on that side of things, right? So construction technology now is really just increasingly operated at a connected system, right? In the 20th century, tall buildings are requiring more than steel frames. They also need elevators now, the foundations, the fire protection, enclosure systems, utilities, and codes that have to be addressed. With dense occupancy in one space, there's large infrastructure requirements, heavy equipment, material production, surveying, transportation, public financing. Oh, there's a fun one. Public financing. Yeah, or public, bid. I don't know how many of you, if you work for contractors, I remember we've had so many jobs where if it's public funding, I don't know where they came up with this idea that they think this is great, but any job that requires public funding, they think it's a benefit to the taxpayers if they pick the low bid. You hear this idea when you go bid a project, it's, the low bid wins, right? So the low bid that a contractor gives is the one that's going to win out. And with public jobs, any public funded job, that's usually the only answer. So usually they have to legally go with the low bid because you're saving the public money. The problem is, I don't think I've ever seen it work out that way. That's actually the case, because usually if there's a low bid, a lot of times something was missed. The bid wasn't complete. There might have been something missed. There might have been something that was lacking. So it always turns into change orders and more cost in the sense that actually gets taken on by the owner and therefore the taxpayer. So it's not always the best system to deal with when we're thinking about this. Okay, so again, this idea of kind of more standardization in the process is really overlooked sometimes because it's less visible, right? So, a crane or a bridge, that's a visible piece of thing, but all that standardization behind the scenes, you don't really see that out front, but it's all part of the process now. Things like standard dimensions, product testing, building codes. My brother-in-law was just working on a building. I forget where it's at, but they had a lot of med gases. This building has tons of med gas lines running through this building, and one of the things they have to do before they can move on to basically the closing in of things is run tests on all these different lines, right? So they're running pressure tests, they're running leak tests, and he has to pass everything. There's very stringent rules for getting past this, and he's managing a job that's been really stressful because there's lots of piping, lots of things going into it, and he's got to get it passed. So lots of things you have to meet now, get different inspectors coming in to check work, all of that type of stuff. U.S. interstate highway system also illustrates a scale through repetition, right? Similar materials used all over the place. Details, there's signage that is consistent across the board. A stop sign here looks the same as it does here, as any other state basically you go to. Construction process could be delivered across many states while adapting to kind of local conditions. Large dams, airports, hospitals, and industrial facilities also depend on organizations capable of coordinating thousands of decisions. Okay, so lots of thought goes into this, lots of coordination has to go into all of these things. The main shift here is that building and infrastructure projects are no longer an isolated object. It's all part of a technological, regulatory, financial, and logistical network. The need to coordinate that network sets the stage for digital information systems. So again, it's not always just about, we're doing the same process of building the same building that we did in ancient days. Now there's all sorts of stuff in the way. There's checkpoints, there's submissions, there's the people that have to come sign off on things. There's this huge system of construction. It's not simply just building something up. I just had a tree fall on my house this weekend. Well, it was a big branch off a giant oak tree. So I have to deal now with insurance. I got to find someone to possibly fix it. I got a deductible. Maybe I want to fix it myself. I don't know. So all that stuff goes into play here, right? So how does that all logistically work out? So it's all the systems that kind of play into this have also made the whole processes for construction a lot different than it used to be, a lot more involved. So, this is kind of looking at this idea again, when this information, became a construction really material, right? So we go from this idea of drawings, okay, that we did manually by paper, and we're kind of moving from that to allow ourselves to do more complex things in a more digital world, right? So we still solve complex problems on paper, and we used to do less drawings probably than we do now. But the idea is that we need to still produce these. CAD just made geometry editable in digital files as opposed to you had to take an eraser and erase things off the paper, right? So CAD just made it to where we went into the digital world. Teams could revise things, they could duplicate, add layers to things very easily, and then transmit basically those drawings in a lot better fashion, right? So we went from this idea of paper that had to be drawn on, revised, marked up, delivered, then hand delivered or delivered by, I don't know, horse and buggy, depending where you were, to now we can just email a file right to someone. Funny enough, though, we still, even though we have all this technology right now, we still live in a world of PDFs. It's always a funny conversation I have with people. Like, at the end of the day, I have all these complex models and analysis software and all these different tools we use in the process. But at the end of the day, you still end up with a two-dimensional PDF of documents, right? Really nothing different than what we did before by hand. You still end up with this state of 2D flat drawing work that gets shared around. It's just how we share it, how we develop that set has drastically changed from one slide to the other. I'll start losing my voice this semester, I can tell. It's going to happen, always happens. All right. So, construction technology, expands capability, but the capability must be paired with production, right? So the historic photographs of like high-rise construction, you usually see workers on exposed steel with very little fall protection, right? All these famous pictures, you see these black and white photos of all these folks walking around, hanging off steel buildings, eating their lunch that you would never think of. And a lot of times we look at those as really heroic, like, it shows like a certain time in history. But they also document a level of acceptable risk, right? That should not really be romanticized in that sense too. Nowadays you look at the people on the right, and we have all this sorts of stuff for fall protection, tie-off systems. There has to be shoring. There's got to be, catch protection systems on high-rise buildings. Modern safety is one of those systems that plays into what we do now, right? So personal protective equipment matters. But so do the guardrails, the engineered anchors, the access planning, equipment inspections, training is a high thing to understand, how we do things, how we use certain tools, communication, sequencing, and really a culture that allows hazards to be reported and corrected. How many of you have like a safety meeting if you work for a contractor on a regular basis, right? It's a requirement. You have to be there. Anyone watch, who's the guy on TikTok or Facebook? God. He's the funny contractor guy that I forget his name. I'll have to look him up. I played some videos of him last time. He always talks about the safety meetings and Ricky. Remember, was it Ricky, the guy on construction site? Anyone knows? Am I dating? It's not that old. I'm not that old. Anyways, I'll pull some of those videos up. It's fun to watch. Yeah. So again, safety is a big deal. Technology can really introduce new risks. Right? A faster machine can expose more people in a work zone if it's poorly controlled. Digital model can create false confidence, right? So we talk about this a lot, how we have these models and we do all this stuff, but you can have this kind of false sense of confidence of how that's actually working, or that, yeah, we answered that question just because it's in the model, right? So that's something you have to pay attention to. Automation can separate workers from hazards, which is great, but only when the process, the maintenance, and the human oversight are well designed, right? So all of that still plays a key part to this. I think a key phrase for this is really just like controlled risk, right? Construction cannot eliminate every hazard, but the industry can identify hazards. They can design controls, train the people properly, and learn from whatever incidents that happen. So when evaluating like an innovation, always ask not only what makes it faster or cheaper, but also how it changes the risk profile of the work. All right, so if I could bring this back kind of to just the questions here on the side, right? So I want you to think about this whenever you're going through this writing assignment and picking some stuff to write about here, and the research is, every innovation, what did it make possible, right? So if there was an innovation in a certain building technology or a building that drove innovation, what did it really make possible, right? So Roman concrete, was able to enable large durable forms. Industrial iron and steel enabled new spans, frames, and heights. Steam equipment obviously moved a lot more material. And then standard components accelerated assembly. Digital information supports faster revision and coordination. Those all play into kind of what did innovation make possible. The next one here is kind of what new coordination did it require, right? So just because we have an innovation in material or technology, how we do things, what else did that require, right? So what type of new coordination? A material might need a supply chain and a construction method. A machine needs operators, maintenance that we talked about, access and sequencing. Prefabrication needs dimensional and control and logistics, where building information modeling needs standards, model responsibilities, reliable updates, and also access to it in the field. And then also think about kind of what risk did it possibly reduce, right, or create. Obviously, our job sites have gotten safer over history, right? We've built in a lot of safety. I think there's a video on the content this week that talks about how unbelievably unsafe job sites were and how safety and standards and regulations that we all maybe get annoyed with nowadays have made it so much of a better place to be able to work. But again, iron framing, think about iron framing, how it addressed some fire concerns while introducing connection and fire protection challenges. Machines reduce some physical labor, but introduced equipment hazards, right? Digital systems can reduce clashes while creating dependency on data quality and version control. So that's always something to kind of think about. Answer these kind of as you're thinking and picking a topic for this written assignment. Kind of think through some of these questions when we're doing this. It'll kind of help, I think, guide you through that. But yeah, questions about anything so far?